Good day, everyone. This is Dr. Soper here, and today I'd like to talk to you about a technique that I've been developing called greedy cross-validation, which can be used as a basis for rapidly identifying optimal or near-optimal machine learning models. To begin, I'll provide a brief introduction and will explain why this is such an important problem. When developing machine learning-based solutions, it's common practice to test a variety of different models with a view toward identifying the model that yields the best performance. The term model, as I'm using it here, refers to a combination of a specific machine learning algorithm and the particular values that have been chosen for the algorithm's tunable or definable parameters. Machine learning practitioners often need to test hundreds or even thousands of different models before deciding upon a final model to use for an analytics or data science project. This is problematic because testing model variance is both time-consuming and computationally intensive, and can hence be very expensive. Some state-of-the-art machine learning models, for example, can take hours or even days to train. Since testing a large number of models can be time-consuming and expensive, many researchers have considered the problem of how to find the best performing model as quickly as possible. Examples of approaches that have emerged from these efforts include Bayesian methods, gradient descent methods, evolutionary approaches, population-based training, and so on. Despite their variety, all non-trivial existing methods share a common general strategy. Specifically, they all work by trying to identify relationships between the model parameters and whatever performance metric is being used. They then use that knowledge to test models that lie within promising regions of the search space. In contrast to all existing methods, greedy cross-validation takes a completely different approach to finding the best performing model as quickly as possible. Rather than trying to find promising regions within the search space, greedy cross-validation instead focuses on the process of measuring model performance itself as a basis for quickly identifying optimal machine learning models. Recall that a model is a combination of a specific machine learning algorithm and the particular values that have been chosen for the algorithm's tunable or definable parameters. These parameters can be structural, for example, the number of hidden layers or the number of nodes per layer in a neural network, or they can be algorithmic settings that control the learning process, for example, the mini-batch size or the learning rate. Collectively, these structural and algorithmic parameters are referred to as the model's hyperparameters, and the task of searching for the optimal combination of hyperparameter settings for a particular machine learning problem is referred to as hyperparameter optimization. Here we see a simple example of searching for an optimal model via hyperparameter optimization. In this example, we have two hyperparameters whose different values are represented by the horizontal and vertical axes. Each orange square represents a specific model, and as we can see, each model has its own unique combination of hyperparameter values. To determine which model is best, we simply evaluate the performance of each model and then retain whichever model exhibits the best performance. In case you're interested, this simple method of hyperparameter optimization is known as a grid search. So we want to choose the best performing machine learning model. But how can we estimate how well a model will perform in the real world? The most common solution to this problem is to test each model using data that it didn't see when the model was being trained. This is the purpose of k-fold cross-validation. Here's how k-fold cross-validation works. First, we randomly split the training data into k subsets. These subsets are called folds. Next, we train the model using all but one of the folds. We then test the model's performance using the remaining fold. Finally, we repeat steps 2 and 3 until each fold has been used exactly once to test the model's performance. When all of this is finished, the model's overall performance is calculated as the average of the performance values obtained from each fold evaluation. Let's see visually how k-fold cross-validation works. In this figure, we'll be testing a single machine learning model using k equals 10 folds. The orange square represents the portion of the available data that will be used for testing the model, while the blue squares represent the portions of the data that will be used to train the model. As you can see, we use each fold of data exactly once to test the model, with all of the remaining folds being used to train the model. This process yields a performance value for each evaluation, and the model's overall performance is calculated as the average of these k different performance values. The example that we just saw considered only one machine learning model. Remember, however, that we want to evaluate many different machine learning models so that we can choose the best one for the problem at hand. Now that we know how standard cross-validation works, we can see what role it plays in the overall hyperparameter optimization process. In this example, we'll evaluate 9 different candidate models using standard cross-validation. As you can see, each time we evaluate a fold for a particular model, our current estimate of the model's performance is updated. After we've evaluated all of a model's folds, we arrive at our final estimate of the model's overall performance. Once we've completed this process for each model, we are able to identify which of the candidate models is best. In this example, Model 5 ultimately turns out to be the best model. It is very important to note, however, that we are unable to reach this conclusion until every model has been fully evaluated. Now that we understand the role of standard cross-validation in the hyperparameter optimization process, we're ready to consider an alternate approach: greedy cross-validation. Rather than evaluating all of the folds for each model in sequence, the greedy cross-validation method works by iteratively evaluating folds for different models, with the specific fold to evaluate next being chosen at runtime based on the current mean performance for each candidate model. After initially evaluating one fold for each model, the next fold to evaluate is simply the next available fold for the model with the best current mean performance. Let's see how this works. Here we have the same example as before, using the same 9 candidate models and the same data. The true ranks of each model are provided for our convenience, but the greedy cross-validation algorithm would certainly not know this information in advance. Now, let's see how the greedy cross-validation algorithm actually works. As you can see, rather than evaluating all of the folds for each model in succession, greedy cross-validation begins by evaluating the first fold for each candidate model. This yields a partial performance metric that indicates our current best estimate of each model's performance. From this point forward, the greedy cross-validation method simply pursues the next available fold for the model with the best current performance. In this particular example, the best current performance is for model 1, so we would next evaluate fold number 2 for that model. After evaluating that fold, the currently known mean performance for Model 1 is updated. In this particular example, Model 1 is no longer the best prospect, but instead, Model 5 is now exhibiting the best current performance. We would therefore evaluate fold number 2 for Model 5 next. We continue by greedily pursuing the next available fold for whichever model exhibits the best current performance at that moment in time. In this case, that model continues to be Model 5, so we continue evaluating its folds until the model has been fully evaluated. As an aside, note that in this example, the first model to be fully evaluated also happens to be the best overall model. If we imagine all of the dark blue squares as the total potential amount of work remaining, we can begin to appreciate that in this case, the greedy cross-validation algorithm was able to identify the best candidate model quite quickly. If we allow the greedy cross-validation algorithm to continue running, we'll see that it tends to complete its evaluation of the best candidate models much sooner than the models that ultimately end up having the worst performance. This is the key point about greedy cross-validation. In comparison to standard cross-validation, when you use greedy cross-validation, the best candidate models will, on average, be fully and completely tested much sooner than the worst candidate models. Theoretically speaking, with standard cross-validation, we should identify the best candidate model on average after evaluating 50% of the search space. With greedy cross-validation, however, we will, on average, identify the best candidate model much sooner. Why does this matter? Well, in the real world, most companies and machine learning practitioners have a computational budget. You may, for example, want to test 1,000 different candidate models. Testing machine learning models is expensive and time-consuming, however, so you may only have enough time or money to test, say, 200 of those models. Given your computational budget, you're much likelier to identify the best model among the 1,000 candidates by using greedy cross-validation than standard cross-validation. Naturally, these ideas need to be evaluated scientifically. A series of experiments was therefore conducted to evaluate how quickly the best model can be identified using greedy cross-validation as opposed to standard cross-validation. For these experiments, 3 different machine learning classifiers were applied to 3 different datasets. All of the classifier algorithms and datasets are open source and publicly available as part of the Python scikit-learn library. For each combination of classifier and dataset used in the experiments, different numbers of models and folds were used for the greedy and standard cross-validation methods. Each candidate model varied from every other candidate model according to the values of its hyperparameters. 30 iterations of each experiment were carried out for each combination of classifier, dataset, and N in order to ensure that the results were statistically stable. So, let's see some results. Here we see a comparison of how quickly the greedy method was able to find the best model in comparison to the standard method for 3 different classifiers on the Boston home prices dataset. As you can see, greedy cross-validation was much faster than standard cross-validation at finding the optimal model in these experiments. Here are the results for the Wisconsin diagnostic breast cancer dataset. Again, greedy cross-validation is much faster than standard cross-validation on average at finding the optimal model. We again see similar results on the optical recognition of handwritten digits dataset, providing additional support for the superiority of greedy cross-validation. Here we see results for different numbers of candidate models on the Boston home prices dataset, averaged across all classifiers. Note that the standard cross-validation method must fully evaluate an average of 50% of all the folds, which precisely conforms with theoretical expectations. Note also that the greedy cross-validation method is consistently faster than the standard method, regardless of the number of candidate models being considered. Again, we see similar results for the Wisconsin diagnostic breast cancer dataset, as well as for the optical recognition of handwritten digits dataset. Finally, we can consider the average time to find the best performing model across all classifiers, all folds, and all candidate models. As shown in this table, the greedy cross-validation method is consistently superior to the standard cross-validation method in terms of its ability to quickly identify the best machine learning model among a set of candidate models. These results are also highly statistically significant. In conclusion then, the results of the experiments indicate that the greedy cross-validation method clearly and substantially outperforms the standard cross-validation method in its ability to quickly identify optimal machine learning models. Put differently, the greedy method allows best performing machine learning models to be identified using a much smaller computational budget than the standard method. This translates to huge potential savings for companies in terms of time and money, or substantial gains in competitive advantage, as well as major benefits for AI and machine learning researchers. Finally, there are many interesting ways in which this research can be extended. For example, the greedy cross-validation algorithm could be readily modified to operate in situations without a strict computational budget, for example by determining on its own when to stop searching. It is also feasible for greedy cross-validation to be integrated with other existing methods of hyperparameter optimization, thus potentially yielding even greater performance. Well, my friends, thanks very much for watching. If you'd like to learn more about greedy cross-validation, I encourage you to read my journal article on this exciting technique. You can find a link to the paper in the video description below. Until next time, have a great day.